Okay, so now let's understand about this vector database. Okay, so whatever the embedding that we have actually created till now, right? So that actually come under the category of dense embedding, right? And all those embedding has to save into in some kind of a database. Okay, so for that, okay, all this embedding saving it into some database, all this embedding as a in terms of vector, okay, that will be saving it into the database, and we normally named as a vector database, right? So what is actually vector database? Okay, vector database is just a storage system in order to save your embedding, okay, in order to save your all your knowledge base. Okay, now there are actually two type of vector storage. The first is you can actually go and take some cluster by paying your own credit, okay, and then later relaunching it. Okay, so you will be having some kind of a open source, okay, where you will be having some storage, let's say 1 GB or 2 GB as a free storage. Every user will get provided. And other than that, suppose if your data is that much big, then you need to actually manually extend the cluster size so that you can actually save all your embedding into the vector database, right? So these are actually the few open source very popular. So like we have a lot more open source vector database as well, but these are actually the very popular. Okay, now when I say these are actually very popular, why? Because these has some kind of very good compute. Okay, these has very excessive good RAM. Okay, and then wherever their server is, okay, so they have actually managed it in a very clean way. Okay, so that is why the reason that these are very popular. Okay, in that sense. Okay, in order to storing, and then security wise also, then it is also much more secure. Okay, then when it comes to latency wise, okay, so these are actually the top, very top open source vector database, okay, which are like quadrant, waviate, milvus, chromadb, and then your postgres vector database. Okay, similarly a postgres, even like mongodb is also there. Okay, even you can actually save your like all this embedding into the mongodb as well, right? Then when it comes to the closed source embedding, suppose that if you in your company like you don't want to save it into the cloud, okay, then you can actually save it into your local server as well. Okay, so you need to have that much local space where you can actually like try to save all your embedding into your local storage as well, right? So you have something called as pine code. Even like in even in local postgres also you can actually save the database. Even like local mongo, the atlas as well as compass version also you can actually save all this embedding, right? I will show you that how do you actually save the embedding once we come into the implementation part. But for now I would just wanted to say you that what is about vector database. Okay, so vector database is just a storage capacity of saving your let me write, right? Okay, so what is basically a vector db? So vector db is just a storage capacity of saving your storage capacity saving your embeddings, right? So let's say that you have some kind of a disk memory space, okay, that some cluster you have already taken. Okay, let me just use some open source vector db. Okay, so let's say that I have actually taken some quadrant. Okay, so in the implementation section I will also like take you towards the journey of that how you can actually create the cluster and other thing. But for now just you can understand the, because this will be common with the other vector database, the same exact the same way. Okay, so let's say that these are actually the one cluster. Okay, this is let's say the m1 cluster that you have actually like taken it or consuming it as a user. Okay, so inside this cluster let's say that you have actually created one collection. Okay, so let's say that you have actually created one collection, and inside this collection you have a set of, let's say, space, okay, where you will be saving your embedding. So let's say that this is your collection, and inside this collection let's say these are basically the index. Okay, and these are actually your saved embedding. Okay, here you will be saving your embedding. Okay, so let's say that these are my index 0, these are my index 2, these are my index 3 up to let's say that index 99. I am actually saving my embedding here. Okay, other than embedding I am also saving my other metadata. Okay, metadata means what? Metadata means like the mapping of the embedding with the word. Okay, these things, right? So let's say that I have actually saved all this chunk. So initially I have a chunk. Okay, all this chunk I am actually giving it to the embedding model, so that every chunk which earlierly it was containing the set of sentence, okay, the set of token, after giving it into the embedding model, every chunk, every word, every token will convert into the some kind of a numeric format. Okay, so that all this format has to save into some space. Okay, and that we named as a vector database, right? Now this is how, let's say, all my embeddings, okay, all my embeddings of the chunk, okay, chunk by chunk will getting saved over here, okay, serially. Okay, so let's say that I have, let's say, 1000 chunk. Okay, it means that let's say if the space of the first, let's say, the array, okay, of this index 0, okay, it is, let's say, 10. Okay, which means that every 10 chunk you are going to save, okay, serially, every 10 chunk you are going to save, right? So you are going to take the every 10th chunk, okay, and then you are going to save it into the vector database, just like this. Okay, now when it comes to after saving, okay, after you complete your saving entirely everything into the vector database, now how does this work? Okay, because once you have a retrieval, right? So retrieval, the first stage of the retrieval is do the embedding and saving into the vector database, right? Now whenever you're actually saving it, just understand the very few keywords, okay, that what kind of embedding that you're actually saving. See, there are two kind of embedding, okay, this I want to highlight as well. So there are basically two kind of embedding structures, okay, which you wanted to save it into the vector database. The first is the dense embedding. Okay, the first is what? The first is basically the dense embedding, which means that you have a set of, let's say, word. Okay, you have a set of word, you wanted to give it some embedding model, and then these word is converted into the chunk, and every chunk will be converted into some kind of a embedding. Okay, so these are basically the dense embedding, where each value of those chunk will be containing the number, or each number is actually mapped to its own corpus text. Okay, to its own text, right? So let's say these are basically the dense embedding. Okay, so and other kind of embedding is that we also do sparse embedding. Okay, sparse embedding. Now what does this sparse embedding will do? Okay, so sparse embedding will make your searching more faster. Okay, and then the third is basically the hybrid. Hybrid means what? It is just a combination of dense as well as sparse. Okay, I will tell you that these are basically the searches, like the searching approach. Okay, these are basically the searching approach. Again, let me tell you one more time. Okay, but before that, let me also tell you, like, first let me tell you about the sparse. Okay, what is basically sparse? So sparse is basically lying between the 0 and 1. Okay, and between 0 1, it's mostly containing the more number of 0. Okay, it will be mostly containing the more number of, let's say, 0 and few number of non-zero. That's it. Let's say that I have the word, let's say I am teaching generative gen AI, right? So when it comes to I, right? So I, let's say that the dimension that I have already defined for I is actually 512, which means that 0 to 511. Okay, in this 0 to 511, let's say that very few part I will be having, let's say, 0.22, 0.49, and the rest of the part is basically 0. Similarly for I am 0.63, and then rest part is, so in more I have the more magnitude of zeros. Okay, and I have very few limited non-zeros category, right? Whenever, like, when I'm actually doing this sparse embedding, right? And when I'm actually doing the dense embedding, now what does the dense embedding will do is that I will be having a more number of non-zero, okay, and very less number of zero. Okay, so these are basically the difference between the embedding structure. Okay, now as a user, like, what kind of embedding you should do? Okay, so research says that you need to save the dense embedding as well as the sparse embedding into your vector database. Why? Because it will make your search much more relevant. Okay, it will make the vector search much more faster. Okay, so why it is needed? Now suppose whatever the user has actually asked, okay, and let's say that vector database algorithm, the retrieval algorithm, not always like perform the semantic search. Okay, if I am actually able to find the word which is like mostly related to the keyword oriented, okay, that I am actually asking a question, and then the question itself is containing a very good keyword, that from the keyword itself I will actually able to pass my pointer to the data in my vector database, then I don't need to like further look for the semantic part. Okay, after like pointing my pointer to my, let's say, retrieved region, okay, then to the nearby area I actually find out this semantic part. Okay, but other than that, let's say that from the keyword itself I would able to find out that within this region my answer, the presence of answer, the probability of the answer presence would be there, okay, within this region, just by like getting the keyword possibilities. Okay, so from, if you're actually doing the keyword searching, keyword kind of a searching, then you always try to look into the sparse embedding format, because in sparse embedding searching is very faster, because the more number of times you have a zero, right, and very few non-zero you have, right? So that is why at the very first part you are supposed to do this keyword search. Okay, and once you actually like understand, so once you actually like able to pass your pointer, okay, pass your retrieving database pointer to this reason, then you will go and find out the reason which is like nearby to it, because I know that there will be a more possibilities of finding the best relevance answer by, like, if I'm going above and if I'm going down, right, I can actually pass, like, I can actually find out the most relevant answer in this reason, right? There I can actually like apply the dense embedding. Okay, there I can actually like apply the dense embedding, and I can do the semantic searching as well, right? So for semantic searching, it is always better to follow the dense embedding, and for keyword searching, it is always better to follow the sparse embedding. Okay, and if you are going to combine these things, okay, suppose that if you're going to combine these things, then it becomes the hybrid search. Now what does this hybrid search will do is that generally what will happen, that in my vector db, right, just understand this part, this is very easy and important as well, right? So in my vector db, for every chunk, right, for every chunk, so let's say that these are my chunk. Okay, these are my chunk in the metadata. So these are my first chunk, let's say these are my second chunk. Okay, and then this is the index 0, this is index 1, this is index 2, right? So let's say, and this is, let's say, index 3. Just understand this, you will get this. Okay, you will get it, I'm sure. Now suppose that if I'm talking about this index 0, right, now what will happen is that index 0 for every chunk, right, in the metadata I will be saving the dense embedding of the entire chunk as well as the sparse embedding. Similarly, for this one, I will be saving the dense embedding plus sparse embedding. I will be saving the dense embedding plus sparse embedding. Similarly, for this one, dense embedding plus sparse embedding. Okay, this I am just telling to enhance the RAG. Like, you can only save the dense embedding itself. Okay, there is no problem in that. But like, why to create a RAG which is much more traditional? Why not to create a RAG which is very enhanced, right? So that is why I will show you the implementation part the both way. Okay, that I am actually like saving the dense embedding, and when I'm doing the retrieval, and if I'm saving the dense embedding and sparse embedding of each chunk in my vector database, and if I am doing the retrieval, then what is the performance at the very like last response. Okay, you will anyway try to understand that like which one you should practice, right? So similarly for this one also, I will be saving this dense embedding plus sparse embedding, and for other as well, right? Now what it will do is that it will make your search very faster. Okay, it will make your search like much more stronger. Okay, your search will be very relevant. Okay, whenever the vector db whenever like these kind of a search will happen, right? So again, what you have understood till now is that, so you have understood about this kind of search that you're supposed to do. Either you're supposed to do this semantic search where you mostly focus on the dense embedding part, either you're supposed to do this keyword search where you mostly focus on the sparse embedding part, or you are doing this we are supposed to do. Okay, in many of this vector database, right, in many of this vector database, we are mostly practicing the hybrid search, which means that it is mostly like storing the dense embedding as well as the sparse embedding into the database of every chunk. Okay, in this way. So we are going to practice this part. Okay, that we will be actually storing the dense embedding as well as the sparse embedding of every chunk in my vector database. Okay, each index by index. Okay, now you got it, right? That what is the structure. Now let's understand about this one, like how do you actually find out the query. Okay, see, you may ask the question, okay, that okay, I can actually understand that till now I am actually saving it in this structure, but you may ask that how can I basically find my data, find my relevant data. Okay, because user is asking a question, right? But how this pointer is supposed to go and point out only that region where my data is basically present. Okay, which searching algorithm that I should apply. Okay, so if the data is already indexed, because in most probably the data is basically your index, right? Which means like there will be index attached to each and every chunk into the database. That happens in most of the normal database, right? Now, because if your data is already indexed, right? So you can actually apply the linear search, but is this relevant? Of course not, because let's say the user is asking some question, right? So let's say that I have one knowledge base, I have created the chunk of this knowledge base, and I have actually saved the embedding of this knowledge base into my vector db. Okay, so let's say that in my vector db it is containing my all the information of my camera. Okay, all the information, let's say index all the information of my camera. Okay, now let's say that user is asking any question. Okay, let's say that user is supposed to ask any question, right? User is supposed to ask any question that what is the status, what is the status of camera 44. Okay, this is the first question. Then let's say that user asked the second question, what violation has occurred, what violation has occurred in camera 54. So suppose that user asked these two questions. Okay, let me change the color. Okay, so suppose that user has asked these two questions, right? User has asked this question and this question. So if the user is asking this question, right? So first of all, what I am going to do is that I need to first convert this question. I need to pass it into my embedding model, right? Embedding model. I need to pass these into my embedding model so that every question is now converted into some kind of a number representation this way, right? And then I need to give it into my retrieval. Okay, and then my retrieval is going to like connect it into the vector database, vector db, and in the vector db it is supposed to give like search and give me the best relevant answer. Okay, now the question is that how does this searching happen. Okay, the first step is that we can actually do the linear search. It means that these are my embedding, right? These are my user embedding. So what it will do is that it will take this embedding and it will search one by one the cosine similarity. Okay, it will search at the index 1, it will find out the cosine similarity, it will search the index 2, it will find out the cosine similarity similarly till it reaches the last one. Okay, and let's say that I am taking the top 3 value, which means that I am taking the cosine similarity which has like the most top 3 result of the cosine similarity. Okay, and then in this way I am going to give this final answer to my LLM model, and then my LLM model is supposed to give me the response. But this is going to take the order of n time, right? Because suppose if my index is, let's say, 1 million, so I don't need to like visit it every time sequentially again by iterating the counter. Okay, so that is why this basically fails, not fails, but like this is very least used searching method, okay, when it comes to searching in vector db. Okay, so now let's say if you're actually doing the binary search, you already know that it has first my index, like all the data has to be sorted. Okay, and when the data has already been sorted, right, so what will I do is that I will first go and check the cosine similarity of the middle element, and then I'm searching that whether I'm able to find my data at the first part, and whether my, see this one, right? So if I'm doing the binary search, right, so what I'm supposed to do is that whatever is my indexing is, right, whatever is my indexing is, that I'm going to find out the median. Okay, I will be finding out that whether my data is actually present, whether my possibility, right, of having my data, whether it is in the median. Okay, if it is, then well and good. If it is not, then I will be searching in the n by 2, and I will be searching the n by 2. Okay, so the total time complexity would be like searching of this one, and then in worst case 2 of n by 2. Okay, this will going to take roughly order of log n in this way, right? But it is also find out that it has also some kind of a limitation, right? Because it is already algorithm. Okay, it is not like ml algorithm. Okay, because there is no ai in it, right? Because suppose if we actually keeps on increasing the data, then it's not very a good approach to like find out the very relevant data, right? Then the other thing is like finding out the KNN, okay, the nearest neighbor algorithm. You have understood about this nearest neighbor algorithm, right? In my machine learning lecture. Okay, so what does this nearest neighbor algorithm will do is that this is actually somewhat a good score. Let's say that you have your data into the vector database, right? So let's say that you have already an embedding of, let's say, up to 1000. Okay, up to 1000 index. So this is the first part, this is the second part, this is third part, and up till here this is my vector database, and these are basically the possible chunk which is present in your vector database, right? So let's say that these are basically the possible chunk which is present in my vector database. Similarly, up till the last index. Now what will this KNN will do is that it will going to take, right, let's say that randomly I will be having a 3 points. Okay, randomly I will be having a 3 points, right, and then it will form its own cluster. Okay, it will going to form its own cluster, it will going to form its own cluster. Okay, let's say that these are my cluster 1, these are my cluster 2, these are my cluster 3. Okay, now what will happen is that suppose if user is asking question, right, so it will going to first find out the centroid of each cluster. Okay, the centroid of each cluster means like the taking the median of each embedding. Okay, and then by taking the median of user query embedding. Okay, and it will going to find out that which of these are basically like shortest distance of all these cluster. Okay, let's say that I have 4 cluster. Okay, so which of these is basically a very shortest distance, it is supposed to go into that cluster. Okay, so let's say that for in this reason, right, I'm able to get the most number of similarity check. Okay, because median of this, and then the median of the cosine similarity of median of this, and the cosine similarity of median of this cluster is somewhat closer compared to these two. Okay, so I would definitely go and find out this cluster. Now inside this cluster, let's say that I have more than 100 embeddings, or let's say I have more than 100 index. Okay, so I need to again check the 100 index one by one again and again. Okay, in this way also might, so let's say for searching time order of 1, and let's say for 100 embedding I am actually iterating, so I am also like iterating it again and again. Okay, so it is also not a very valid approach. It is a good approach that if you have perfectly machine learning model trained, right, just to like pass your user query pointer to the region, to the cluster where there is a more possibility of finding out the answer, then it is always better, well and good compared to the previous two searching. Okay, but it is also not a very good way of finding out these things. Okay, and most of these modern day vector database are internally not using it, right? So people have actually come up with the very good research based algorithm, which is like the approximate nearest neighbor, which is like actually using this hierarchical navigable small world. Now what does that mean? So because it is sounding a bit bulkier, but it's not. Okay, I will tell you like very simple what it is. Okay, and if you just want me to walk me through the research paper, I will also try to do that. Okay, just let me know. So let's try to understand this thing, the last one, which is like the HNSW, which is like hierarchical navigable small world. Okay, now what is this last algorithm? Okay, and most of these, if you see this, most of this vector database, right, so internally they all are actually using this as by default, which is like HNSW algorithm for searching the best relevant answer from the vector database by default. Okay, so let me just tell you, let me give you the brief logic of this. Okay, I will not go in such detail, but let me give you the big brief logic like HNSW. Okay, so what does this algorithm will tell? Okay, so this is very simple. See, so first of all, it will work on hierarchical level by level structure. So let's say that in my first level, I have, let's say, three level. Okay, I have first level, I have second level, and I have three level. Level three, I have level one, I have level two, I have level three. Okay, now what will happen is that I need to actually find it out. Okay, I need to find out my best relevant answer. Okay, and let's say that I have the user query. Okay, I have a user query which is like in this format, and I need to find my like best relevant data. Okay, now what it will do is that, let's say that these are basically my complete company knowledge database, right? So all these are knowledge base are converted into the embedding, and level by level it is actually set. Okay, so let's say that these are my different embedding which is already saving it, right? So let me give you a very brief example that what does that mean. So let's say that here it containing all the camera information. Okay, then here it is also containing, so let's say that these are basically the camera one. Okay, these are basically the camera two, these are basically the camera three, all these are embedding. Okay, similarly, other than camera detail, now let's say so the manufacturing company information. Okay, the manufacturing information. Okay, these are also containing the different embedding of the different chunks it has. Then it is also containing the dates. Okay, then it is also containing the price of the camera. Okay, these are basically like the information of this camera. Okay, so it is also containing these things. Okay, now the second level, let's say that it is containing the violation information. Okay, the violation information, so it means that it is containing many different type of activity violation. That some will actually violation information regarding the PPE kit. Okay, some information regarding the helmet. Okay, then some information regarding the other accessory, the safety equipments. Okay, the safety equipments and other thing, right? So this is basically the containing the embedding of these kind of a chunk. Okay, these kind of a chunk which is related to this violation information. Okay, and let's say at the very third layer it is actually containing the very, let's say, a very confidential kind of information. Okay, so let's say that very confidential information. Okay, confidential information, let's say that it has some kind of investor details. Okay, investor details, or let's say the kind of the kind of payment that has been transactionally done between the two parties. Okay, so payment information, another thing, right? Payment information and other thing. Okay, it is actually containing these kind of embedding. Okay, the chunks. Okay, now the very interesting part of these things, this hierarchical structure, is that all these things are kind of connected, which means that some kind of a manufacturing detail or some kind of a dates and prices, or let's say the cameras, right? So all, let's say that camera one, camera two, camera three, right? So all these things are kind of connected with the lower level layer. Okay, so let's say that camera 1 and then camera 2 and then camera 3 are associated with the PPE kit. Okay, similarly, let's say manufacturing is actually associated with the many different safety equipment. Okay, just like this. Okay, so this is my this one, and then this is my this one, and then this one. Okay, similarly, let's say that the violation information, the some part of these things are actually like associated with that, which of these companies or which of these investors are actually paying for these equipments. Okay, to the delivering cost and other thing. Okay, so other thing, right? Similarly, let's say that for other information, like what it is like connected with what level. Okay, all these things. So you can understand that at every level, right, it is actually, each level is actually connected to these things, right? Now why it is actually needed is suppose that user is asking any question. User is asking that is the payment what is the payment structure. Okay, what is the payment structure of camera 2 which is deployed in the XYZ client location. So suppose user is asking these question, right? Now these question, first of all, the searching algorithm will going to find it out that whether it is actually available, or whether I will get the some indication of finding out the answer of this question. So it will going to find out in the very first level. Okay, so in the very first level, again, there will be different clusters. Okay, it will going to go to the nearest cluster, and it will going to find it out that whether there is some significance of giving the answer to this question. Okay, so let's say that for finding out this one, so suppose that, so my answer is somewhere belonging to this area. Okay, let's say this cluster, my answer is somewhere belonging to this cluster. So I will have a possibility that some of these points or some of this embedding must be connected to the lower level. So what will happen is that it will going to first scrape out few of those words. Okay, few of those words. Let's say what are the payment structure of camera 2 which is deployed. So it is going to find out the words like camera 2 and the other associated keywords, okay, which are actually related to camera 2. Okay, it will going to find it out and then see that whether how it is actually related to the level number 2. Okay, so it will again jump to this level number 2, the graph format, right? Then in the level 2 it will going to find out that okay, so is it like located to the client location, so it will going to find out the keyword like location. So it will going to find out the location. Okay, so this is actually located to this one, and if I'm going to find out the location, I will going to find out the investor detail, the payment structure, and then after this I am going to combine the level 1 answer, the level 2 answer, the level 3 answer. Okay, and then I'm going to pass it into the LLM so that my LLM could understand each of these embedding which is already mapped with some kind of a words and keyword, and it is supposed to give you the response. Now this is the best embedding, right? Because it is a hierarchical way. Now let me make the task very easy, even if you're not getting this. Okay, so suppose that you are actually going into the new city. Okay, and you have a map. Okay, you have a map, so understand map as a pointer. Okay, understand map as a pointer, right? But that map is not very significant, right? And you are actually entering into the city, right? And some friend is actually given that these are my flat number and you need to come into the destination part, right? So now the moment you're actually entering into the city, right, in the highway region, right, so what you're supposed to do is that you are supposed to take the guidance of the local people which are like present in the highway part. Okay, just to enter into the city. Okay, you're going to ask some local people. Okay, so the local people is supposed to give you that these are the shortest reason that you're supposed to go to avoid the traffic reason of the city. Okay, so by taking the guidance from the local people, you are actually entering into the city, right? Because these local people are connected to the city. Okay, so that is why you're actually entering into the city, right, by taking the guidance. Now once you actually come into the city, right, by avoiding the traffic and other things because of the guidance given by the local people, again you are going to ask the local people of which are actually surrounded in the city. Okay, so the people is going to take that, okay, take the street ABC. Okay, and then you are going to reach to the destination very safely and fastly. Okay, so that after level 2, like from the city region, you are going into the your friend's flat. Okay, the final destination, right? In this way, right, it will also going to work it this way, right? That the searching becomes very very faster because you are actually moving into the hierarchical structure format, right? That is why this approach, the HNSW approach, right, is actually like getting used by so many vector database by default. Okay, and these kind of like searching mechanism into a vector database, as a RAG based expert, you need to know about these things, because in coding I just going to import the one simple library and then all these things will be done very smoothly, right? But what is actually happening inside, you just need to know about these things, right? That how these things are actually working. Okay, so let me just sum up the entire RAG part, right? Let me just sum up the entire RAG part, because till now like you have understood about the entire thing. Okay, let me just sum up and let me bind it into the one like format, like what you have understood till now. Okay, so in the RAG part, right, again going into this diagram, right? So in RAG part, what you will do, first of all, you wanted to make a chatbot, right? So first of all, you want your LLM model, so that LLM model could identify your company knowledge base, okay, your own data. So what you're going to do is that you're going to feed the data. Okay, now whenever you're actually feeding the data, after feeding the data, let's say whether your data is in PDF format or TXT format, okay, you're supposed to give the data. Now the person is going to take your data and then convert and read your data and convert this data into a chunk. Okay, each chunk is going to contain the subset of the sentence, right, which is actually present in your data. You have actually defined the chunk. You have a fixed size chunking, you have a dynamic chunking. Okay, and we see lot of chunking strategy. Okay, so after doing the chunking operation of your data, right, then you need to pass it into the embedding model. Okay, and you have understood about that what kind of embedding model that you're supposed to use. Okay, whether you are use the rule based embedding or a transformer based embedding. In the transformer based embedding, we have learned about the BERT model embedding, right? And we have learned in the BERT model embedding, we know that how to train the BERT model embedding using a MLM, like masked language model, as well as the next sentence prediction. Okay, these two things are basically like helps my chunk to convert into the relevant embedding. Okay, now don't worry, you don't need to train it because these things are already been trained. I will just be importing these things. Okay, just for your knowledge, I'm telling that first of all you convert these things into a chunk, then each chunk, with the help of transformer based embedding model, I will be converting these things into a embedding. Okay, now once I convert these things into the embedding, then I am supposed to save this embedding into my vector database. Okay, now in order to save this embedding into the vector database, there are actually two possibilities, right? So creating the dense embedding as well as the sparse embedding. Okay, for the first purpose, I will be creating the dense as well as the sparse embedding, and with the hybrid search approach, I am going to save these things, right, into my uh, vector database, right? So other than with the chunk, I will be saving the dense embedding as well as the sparse embedding. Okay, so that whenever I'm doing this searching, right, so if I am following the hybrid search, right, then I will do my search more faster. Okay, now there is a other kind of searching mechanism in the vector database in order to search the relevant answer. Okay, so how my retrieval is going to search the information from the vector database. So for in order to search the information, we have understood about that we have a linear search, binary search, hierarchical search, right, and other search, like we have a k nearest neighbor search. And out of all this search, we have understood that many of these vector database, they are actually by default using this HNSW kind of a search method in order to search the relevant answer from your vector database. Okay, and after it has been like fetched, right, the retrieval, okay, the retrieval, once the retrieval is getting fetched, okay, then it is going to pass it into the cross encoder, okay, just to give the relevance score to my retrieved result, okay, so that I can basically skip it. Okay, I can actually apply the matrix decomposition method, okay, the excellent method, and I can basically skip my embedding and I can actually take the top best embedding. Okay, and then I am going to pass this retrieved embedding from the retrieval. Okay, and then I'm going to pass it into the last step, which is like my LLM part, so that my LLM could understand the word which has been fetched, right, by the entire RAG system, and then so that it is supposed to give me the best response. Okay, just in the same way, just like how does the chat GPT work, okay, how does the Google Notebook LLM work, right, how does the any cloud, okay, how does this work? We are actually like uploading our data, okay, day to day data, okay, and we are asking question and it is supposed to give me the answer. Okay, because these are the very significant RAG based system, right, and we will be building the entire thing for our use cases as well, right. I will show you in the implementation part each and everything integrated with the LangChain and the other vector database as well, right. So these are basically the entire theory part which I wanted to cover in the RAG part. Okay, and if you have any question, right, just let me know. Okay, just let me know, just drop it so that I would able to like know that where you are actually facing issue, so that I can actually make the another video on it, right. So these are basically the RAG part. I'm definitely sure that you would have probably revised it this thing, and then you can be a RAG expert, right, because these things are very very in demand in the many of this corporate. Okay, and even in lot of interviews also, people will definitely going to ask, if you're a generative AI engineer, there will definitely one question of one or two question on RAG based system. Okay, so that is why these are the RAG based approach, and we have actually done a lot more thing in RAG, right. So yes, so these are basically the RAG thing, and so let's just wind up entire thing. Okay, and let's move into the implementation part. Okay, so thank you for like attaching your attention to this entire series of RAG theory part. Okay, so that when I come into the practical part and the implementation part, you are going to understand each and everything just like you have understood it till now before. Okay, thank you all.